Okay. All right. So G2, well, let's see. I don't think you can do it with G2. Well, let's say, first of all, you try traveling around all the outer edges first. So you go doink, 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 doink. Well, then you're going to have a problem covering this X without repeating one of those edges that's on the outside. Okay. Now, that's not a proof that there isn't an Euler circuit. It just means it's not going to work doing it that way. All right. Let's see. What did I say here? Neither G2 nor G3 has an Euler circuit. All right. As can be verified by inspection. So you just look at a bunch of possibilities. Let's say that I tried to, I don't know, do something like this. I go down and then I go up this way and then I go up this way. I can cover every edge except I miss the one on the bottom. Right? If I go doink, 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 doink. Right? And then, right, so neither one of them has an Euler circuit. G3 does have an Euler path. If you don't care about starting and ending at the same point, you can go A, C, D, E, B, D, A, B. All right, so you start at A, end at B. That's an Euler path. Okay. All right. So it turns out that there is a nice, easy theorem for figuring out which graphs have Euler circuits and which graphs have Euler paths. All right. Necessary conditions for Euler circuits and paths. So an Euler circuit begins with a vertex and continues with an edge incident with that vertex. Okay. So when you start off at vertex A, figure that you're counting 1 from the degree of A. All right. Each time you visit a vertex, you add a 1 to that vertex. Each time the circuit passes through a vertex, it actually contributes 2 because, for example, if I go from A to B, so 1 for A, 1 for B, and then let's say I go from B to C, I count another 1 for B and 1 for C. Okay. And then the circuit terminates where it started, which contributes 1 to the degree of A. And that means the degree of A has to be even because it started at the beginning where I counted 1 on that one. Now, that vertex might have been visited multiple times in between. So when I started, it got a 1. Every time I passed through it, it got 2. And then at the end, it got another 1. So then, so that means the degree of that vertex has to be even. Okay. And so the other vertices, because they all got passed through, maybe multiple times, they also have to be even. Okay. So the necessary condition for an Euler circuit is that every vertex in the graph has to have even degree. That is a necessary condition for an Euler circuit. Now, if you're happy to have just an Euler path, starting and ending at the same at different points, your initial vertex is going to get 1 when you start, and then it might get visited multiple times. Each time it gets a 2, but it's not going to end there. So it's going to have a bunch of 2s and that 1 from the beginning. So that vertex is going to have odd degree. And the same for the final vertex. It might get passed through a bunch of times, and then at the end, you're going to add a 1. So necessary condition for an Euler path is that if your graph has an Euler path, it has to have exactly 2 vertices of odd degree. And those vertices are where does your path begin and where does it end. Okay. All right, and it turns out that those necessary conditions are also sufficient. Right? So it's an if and only if. Necessary and sufficient conditions are like the greatest thing in the world because they tell you, If your graph has these properties, then it has, say, an Euler path. And if it has an Euler path, it has to have these properties. So they're totally equivalent, those two things. I think that I might like to skip over this for now. All right. This is one of those weird things. I have no memory of where this slide came from. That was probably... let's maybe think about coming back to that. If I decide to come back to it, I'll probably tweak this a little bit, maybe put it on multiple slides. This is kind of difficult to follow right now. Anyway, algorithms for constructing Euler circuits, that might be something to look at later. Okay. All right, so here we go. This is the official theorem. A connected multigraph with at least two vertices has an Euler circuit if and only if each of its vertices has even degree. Oh, that's such a nice, simple condition. And it's necessary and sufficient. If all the vertices have even degree, you have an Euler circuit. If you have an Euler circuit, all the vertices have even degree. It has an Euler path if and only if it has exactly two vertices of odd degree. Okay. So if we come back to the Königsberg problem, you look at the degrees of all these vertices. I'll just take them in alphabetical order. So here's A, it has degree 4, right? C has degree, oh, I'm sorry, you're right, I missed this one. Thank you. That would have gotten me in trouble. That has degree 5, this has degree 3, this has degree 3, this has degree 3. So not only are all of the vertices not of even degree, it's also not true that exactly two of them are odd degree. All right? There are 4 of odd degree, which means that this graph doesn't have an Euler circuit and it doesn't have an Euler path. So it is not possible to have a simple path even where you cross all the bridges exactly one time. You can't do it. Can't be done. Oops. All right, no Euler circuit, and it is impossible to start at a given point, cross each bridge, and return to the starting point. I feel like there's supposed to be more stuff there. Okay. So it explains why there's no Euler circuit. I don't know where the explanation is of why it doesn't have... That doesn't even look right. 2 of the vertices have odd degree. Well, yeah. It's not exactly 2 of them, but... that's weird. I don't get that. Okay. Anyway, it doesn't have an Euler circuit and it doesn't have an Euler path. For a circuit, they would all have to be even. For a path, exactly 2 of them would have to be odd. I'm sorry. Exactly 2 of them would have to be odd. Okay. So here are some more examples. These are supposed to be 3 separate examples. So this is easy, right? You can look at these and just figure out which of these has an Euler circuit, which of them has an Euler path. Right? So just look at all the degrees. The first one, let's call this G1, has degrees 2, 3, 3, and 2. So that has exactly 2 vertices of odd degree, which means it has an Euler path. It does not have an Euler circuit, right? All right. Now this theorem, even though it's great, it's a necessary and sufficient. It doesn't tell you how to construct the path. But one thing that is helpful is you know that the 2 vertices that have odd degree, they have to be your starting and ending points. Okay. So let's see, if we start at B, you could go to, what could you do? You could start at B and you could go doink, 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 right? So how did that go? B, C, D, B, A, D. That's an Euler path, right? Okay. Oh, I just noticed that it says G2 there. You can barely see it. All right, so how do these go? 2, 3, 1, 2, 3, 4, 1, 2, 3, 2, 1, 2, 3, 4, 1, 2, 3, 4. I think that one is also going to have a path and no circuit, isn't that right? 2 vertices of odd degree. Okay, I don't know if I want to take the time to try to figure out what one of the paths is. Maybe we could skip that for now. Let's see, this graph has a name, right? Anybody remember what this kind of graph is called? It's called a wheel. This is the graph W6. Right? A wheel is when you take a cycle and then add a spoke in the middle, what I call a spoke. All right. So all of these outer vertices are going to have degree 3 because they connect to the other 2 outer vertices and they also connect to the spoke. So those are all going to be 3. And then the spoke is going to have degree 6 because it connects to all of the outer vertices. And that's not going to have either one of the things we're talking about, right? It definitely doesn't have all even degree, and it does not have exactly 2 of odd degree. So this is not going to have either one of those things. Right? Okay, questions? I think, okay, G1 contains exactly 2 vertices of odd degree, so it has an Euler path. DAB, oh, okay. So that's, at first I was thinking maybe that's the reverse path of the one I found. It's not exactly, it almost is. G2 also contains exactly 2 vertices of odd degree. There's a path. Okay. And then G3 doesn't have either one of those things. All you have to say is it doesn't have an Euler path. Remember, every circuit is a path. It's just a special kind of path. So when you say there's no path, I'll assume that you mean there's also no circuit. If you want to spell it out for me, that's fine too. All right, so just some little applications that you can read, used to solve many practical problems, such as finding a path or a circuit that traverses each street in a neighborhood, street in a neighborhood, each road in a transportation network, etc., etc. Some other applications. Okay, so I think, yes, that's awful. All right, so we'll stop there, take a little break. And okie dokie. All right, so there are Euler circuits, Euler paths, and then there are Hamilton paths and circuits. And I remember somebody pointing out to me when I was in grad school looking at this stuff that an easy way to remember. So Hamilton is basically does the same thing with vertices that Euler does with edges. So a path that visits each vertex exactly one time is a Hamilton path. And it's a Hamilton circuit if it starts and ends at the same vertex. So in a Hamilton path, you're allowed to repeat edges, just not vertices. Okay, so I tweaked this during the break because it looked really bad. The font was really small. I don't remember what happened. Euler paths and circuits contained every edge only once. Now we look at paths and circuits that contain every vertex exactly once. William Hamilton invented the Icosian puzzle in 1857. I remember the first time I heard this story. It consisted of a wooden dodecahedron, or as you D&D players might know, as a 12-sided die, right? Yeah, which looks like this. So I understand this was also called the Around the World puzzle. Some people called it the Around the World puzzle because so there was a peg at each vertex. The vertices represented cities. And so the puzzle was, can you find a path around the world where you visit each city exactly one time? And the puzzle, okay, so here's a graph representing the puzzle. If you imagine taking this and just flattening it out. Okay. And so when I heard the story, I heard it as it raised this whole really interesting branch of graph theory, but the puzzle itself was kind of a commercial failure because it's really, really, really easy. So the object is to visit each city exactly one time. I think all you have to do is something like this. Just go along there, and then go along here, and then go along there. Admittedly, it might not have looked that easy to the people that were, looking at this three-dimensional thing instead of looking at it like that. But anyway, somebody figured it out. It was really, really easy. It wasn't a bestseller. It's kind of hard to see. Okay, so I guess the edges that are included are the black edges, which or the blue ones. That's really, really hard to see. Okay. Anyway, you saw what I did here, right? Just go along here, and then go along here, and then go along here. That's actually a Hamilton path, what I did. All right, it's not a Hamilton circuit. Okay. All right. But that's what a Hamilton path or Hamilton circuit is. It's a path or a circuit that visits each vertex exactly one time. And what will, I think, always happen is that you're going to skip a whole bunch of edges. All right? You're not going to need to use all the edges. But you will, by definition, use all the vertices. So a simple path in a graph that passes through every vertex exactly once is called a Hamilton path. And if it's a circuit, it's called a Hamilton circuit. A simple path x0, x1 through x sub n is called a Hamilton path if this is a simple path. Okay, that's just a fancy way of saying that all the vertices are included. That's all. Okay. All right. Which of these simple graphs has a Hamilton circuit, or if not, a Hamilton path? Now, unfortunately, I'm kind of happy this is still here. We don't have any kind of necessary and sufficient condition yet for figuring that out, so let's just see if we can figure it out. All right, so starting with G1, so the object of the game is to visit each vertex exactly one time and hopefully come back to where we started. Well, I think, let's see, that might be kind of hard to do with this one. If you start here, you're going to pass through E, and then I don't see any way of getting to A and B without having to go through E again, right? Yeah, so there's a path. There's definitely a path. I don't think there's a circuit, though. Right? Yeah. Okay, but I think the second one has a circuit. I think the second one has a circuit. What can you do? You can go, does it? Let's see. If you go like this, oh yeah, like that, right? And then number 3, I don't think that has either. Let's see. Yes, that's right. So let's say you start at A. If you go A, B, okay, well, it has a path. It does have a path. Oh, duh. Yeah. Right? Yeah.
So the Euler circuit cares about getting through all the lines, whereas the Hamilton only cares about the line.
Exactly. Okay. Right. And with Euler, another difference is that with Euler, if you're having to traverse every edge, you're automatically going to hit all the vertices. And in fact, that's where the big theorem comes from about if there's a circuit, all the vertices are going to have even degree. If there's only a path, then 2 of them are going to have odd degree. So with Euler, you do hit all the vertices. You hit them more than once. All right. But with a Hamilton path or Hamilton circuit, you do not traverse all the edges. There's too many edges. You can't get through all of them, usually. All right. Okay, so G1 has it does have a Hamilton circuit. How does that work? AB, ABC. Am I reading that wrong?
The other one's for G3 is
Oh, for goodness sake. A, B, C, D. A, B, C, D. Okay, I think that's supposed to be for G2. I think that one there is supposed to be for G2, right? How did we not notice that last year? And that's supposed to be G1. I think that fixes it. Just make this G2, make this G1. Right? No, that doesn't fix it because G3 does have a circuit. I bet this solution was supposed to go with a different picture. That's probably what it is. I'm sorry, guys. Okay. All right, so just ignore this. It's probably the safest thing to do. All right. I told you, this is the part where the choreographer died. Okay. Now, it turns out that Hamilton circuits are kind of a harder problem than Euler. So there are some necessary conditions for Hamilton circuits, but I don't know of any known sufficient conditions, I think is the way it works. There is no simple necessary and sufficient conditions that are known. Okay, there are some necessary conditions, though, and those are named after these guys. So there's Dirac's theorem, which says that if you have a simple graph such that the degree of every vertex is at least n over 2, where n is the number of vertices. So basically what that's saying is that if each vertex in your graph is connected to at least half of the other vertices, then you're going to have a Hamilton circuit. All right. Does that make sense? If each vertex is connected to at least half of the other vertices. I'm going to have to double check. I don't remember how simple the proof is. It might not be that simple. I'll check though. I don't know that I can off the top of my head.
So you have both a Hamilton and a Thorne?
Say that again?
You have both a Hamilton and a Thorne graph? Or are they mutually in?
Well, remember that Euler and Hamilton, they don't describe graphs. They describe paths or circuits within the graph. No, you can't. No, there can't. A path cannot be both Euler and Hamilton because, Todd, a Hamilton path visits each vertex one time, whereas Euler visits it multiple times. So I don't think it can be both.
Or not, what if
Right?
you just have a triangle? You just,
Oh, yeah.
if, yeah, you just had a triangle.
No, that's right. A triangle does it.
Yeah.
Yeah. Okay, but I'm thinking that if you put a couple of extra conditions on there, like if you said, you know, the thing has at least, it would actually work for any cycle, right? Yeah, any cycle. Yeah. Well, like I'm thinking that if you had some extra condition that said that there were at least a certain number of additional edges other than those.
And maybe if like the degrees are all the same, maybe that's it.
Right. And then we're getting at, because remember Euler, for a circuit, they're all even or exactly 2 or odd. Right? That gives you a circuit, that gives you a path. Okay. So I take it back. Yeah, there are some examples like those. This would be Euler and it would be Hamilton. Let me think about this for one more second. So Hamilton, it has to visit every vertex exactly one time. Let's say you had n vertices. That means that you're going to go over a total of, let's say it's a circuit. All right, so you begin and end in the same place. A Hamilton circuit is going to go through n vertices, and it's going to go through n plus 1 edges? No, I guess n edges. Right? 1, 2, 3, 4, 1, 2, 3. So I'm thinking that if you have even one more edge than you have vertices, that then it couldn't be both Euler and Hamilton. I'm having trouble thinking of any examples other than cycles that can be both. Oh, right. Right. Well, it's a good question. It's a little deeper than I realized. Okay. So again, Dirac's theorem, if each vertex connects to at least half of the other vertices, guaranteed you'll have a Hamilton circuit. And then Orr's theorem, and I'm not 100% sure I'm saying that correctly. I think it's Orr. If G is a simple graph with at least 3 vertices such that you take any pair of non-adjacent vertices and those degrees add up to at least n, and I have examples of this, by the way, then that graph has to have a Hamilton circuit. Okay. Where are the examples? I think they're in the other. let me dip into, I'm not going to post the notes right now. I just want to see, I think I might have examples in my other, which one is this, 10.5? Let me just pull this up real quick and see if I have examples for just that. I think I do. So this was the thing I threw together at the end of last semester. Let me just look in here real quick. Oh, okay. Perfect. Okay, so I had started off with a reminder of what Dirac's theorem said. So if G is a simple graph with at least 3 vertices such that the degree of every vertex is at least n over 2, then G has to have a Hamilton circuit. So you can use that to show that this graph has a Hamilton circuit. I mean, I think it's easy enough to just draw one for this. But there are going to be other examples where maybe it's very difficult to actually come up with the Hamilton circuit. Let me see. Can I draw that? If you went this way. Oh, yeah. It's easy to just draw that. But you can also use the theorem to prove it exists. So if you, let's see. So 1, 2, 3, 4, 5, 6. It has 6 vertices. So as long as each vertex is degree at least 3, Dirac's theorem says there has to be a Hamilton circuit. And I think that's true, right? Aren't they all exactly 3? All right, there you go. Now remember, Dirac's theorem is a necessary condition. It's not a sufficient condition, which means that there are going to be graphs that have Hamilton circuits that have some vertices with degree less than n over 2. All right? Okay. All right, so here's another example. This is to illustrate Orr's theorem. So Orr's theorem is a little different. First of all, notice that I would not be able to use Dirac's theorem on this one. This graph has 5 vertices. N over 2 is 2.5. And so the way that works is, in order for Dirac's theorem to work, each vertex would have to be degree at least 3. All right? Because degree 2, that's not at least n over 2. Right? So you'd have to round it up. And here's a vertex of degree 2. So can't use Dirac's theorem. But you can use Orr's theorem because I think every other vertex is degree 3, isn't it? And so what Orr's theorem says is that if every single pair of vertices adds up to at least n, then you're guaranteed to have a Hamilton circuit. And that's true, right? I mean, that's clearly true. When you take any pair of vertices, either you're going to pick the 2, and then any other vertex you put it with. So let's put it like this. I think that I can even... for all, let's call these vertices, let me call them U1, and then we'll, you know what, just call that U, actually. Call this U, and then call these V1, V2, V3, V4. For all I from 1 to 4, the degree of U plus the degree of V sub I is exactly 5. So, and then if you don't pick vertex U, for all I and J, this is a geeky way we talk. Well, you do this in computer science, right, in programming, right? When you're doing a double loop, so that you don't get repeats, you just force one to be less than the other one, right? The degree of V sub I plus the degree of v sub j is exactly 6, which is greater than or equal to 5. Okay. Kind of totally belabored the point there, but right. Every pair of vertices adds up to at least 5. That's what it is.
Is there like a lexicon of mathematics that says, okay, this form means that we're trying not to get duplicates? But I've never seen that before.
Really?
Yeah.
You don't use that in programming? Like, well, you do. It just doesn't look like that. The way that you say that in programming is something like this. Now, remember, I'm not a programmer, so this might look ridiculous, but you say something like, for I from 1 to 4, and then you say for j from 1 to I. Let me see. I think I might have that backwards. Yeah, I have it backwards. This says the same thing as that.
Yeah, they teach us not to do that.
Really?
Unreadable, yeah.
Oh. Okay. Well, we do it in math. We don't mind doing it. So this is saying, it's saying, okay, we're going to all agree that the I is going to be less than the j, which means they won't be equal. And the other thing it does is you're not going to get duplicates, like you're not going to get I to be 2 and j to be 3 and also get I to be 3 and j to be 2. That's not going to happen.
I'm sure that's happened somewhere. I just glossed over it because I had no idea what it means, but that makes a whole lot of sense.
Oh, okay. Well, I'm glad that happened then, because I just popped into my head. But it did belabor the point. I mean, since we only have 5 vertices, you only have 10 different pairs of vertices. It's easy to just check them, especially when only one of them has a degree that's different from the others, right? You're either including the 2 or you're not. If you include the 2, then any 2 are going to add up to 5. And if you don't include the 2, then any 2 are going to add up to 6. That's it. Okay. Yeah, okay, I'm not ready to talk about this yet. Okay. That's all I have for right now. Dijkstra's algorithm will probably take up quite a bit of time on Thursday. That's always fun. So Dijkstra's algorithm is finding, it's kind of sort of related to your traveling salesman problem. It's about finding a path of least weight from one place to another. All right. So applications are like you want to minimize the distance or you want to minimize the cost. I have an example where the weights are airfares between one city and another.
That's the airplane thing?
Yeah. Yeah. Okay. So we'll talk about that on Thursday. All right. You technically own me for 15 more minutes. I'd be happy to go over any of the... There were a couple, like 2 or 3. It's still recording.